Thank you, Alain, for the nice introduction, and good morning, everyone. So today I'm going to present you the results we have obtained with my colleagues Vincent Derbemont and Emmanuel H at IFPN regarding the estimations of the total metal requirements for batteries for electric vehicles. Briefly, a few words on IFPN. So IFPN is a French research and innovation institute, partially funded by the French government, and that operates on the scopes of climate and environment and circular economy, renewable energies, responsible oil and gas, and sustainable mobility. And that's concerning that last topic that I'm going to present you the results today. So few elements of context, of which I'm sure you are all very well aware of. The context is the one of the exponential increase of the electric vehicle sales, both battery electric vehicles and plug-in electric vehicles. Their sales have been multiplied by 100 over the past 10 years. And on that share, battery electric vehicles represent 70% of the total sales. The issue that is linked with that rapid increase or rapid deployment of electric vehicles is the one of the metal content, since battery electric vehicles contain 6 times more minerals than conventional cars. So it's a matter of the total amount of metal, but also of the diversity of metals, since we have much more different metals in battery electric vehicles. And that raises several challenges on reserves or resources, challenges on the total annual production of those metals, and of course also the challenges on the sovereignty of the supply chain. So for those reasons, the European Commission has issued the European Battery Regulation that sets different targets to promote the use of secondary sources of metals instead of primary sources. So there are some targets have been set on the collection rate that are to be between 50 and 60% in 2028 and 2031. There are also some targets regarding the recycling rates for lithium, cobalt, nickel, and copper at 90 and 95% for cobalt, nickel, and copper. The targets are a little bit lower for lithium because it's a little bit more difficult to recycle, and the targets are at 50 and 80% in 2027, 2031. If we combine both the collecting rate and the recycling rate, that's what is done right here, we reach targets of 49 and 58% of the total metal we can recover from used batteries. Apart from that, there are also targets in terms of reincorporation rate, meaning the amount of secondary sources used in the manufacturing of new batteries, and those rates range between 6% for lithium in 2031 to 26% for cobalt in 2036. So the question here, and what we want to address with that presentation is, we see that there will be challenges with the supply chain of the total amount that we can supply for those metals, and the idea is to estimate what are those amounts and what could be the lever to limit the metal requirements for electric vehicles. So for that, we have designed a quite simple model to estimate the total metal demand. So I will first present you that model, and then we'll see what are the results for Europe in terms of battery capacities and metal demand. And after that, we'll see what kind of policies can help lower those demands. So let's start with the presentation of the model. So that's what we call the metal balance model, the MELBA model. And so lots of elements on that slide, but if we go from the left to the right, the idea is to make a link between the total electric vehicle sales on a specific area with the primary metal sources. So if we start with the electric vehicle sales, for each vehicle we can associate 1 or 2 batteries, depending on the duration or the lifetime of the batteries. We can also associate a capacity for the batteries for each vehicles. And we also can define different batteries market shares, depending on the type of chemistries that are included in the vehicles, together with, for each type of battery, a material intensity for those batteries. Once we have done that, we can compute the total metal demand to manufacture all those batteries, and the total metal demand is mainly used to manufacture the battery components, but we also have some scraps due to imperfect processes. At the end of the life of the batteries, they can be collected. We have to define a collecting rate. After the collection, they can be directly recycled, or they can have also a second life, for example, in stationary battery applications. Afterward, they can be recycled. Once we have defined the recycling rate, the second life rate and duration, the collecting rate, we are able to compute the total secondary metal sources that we can get from the recycling processes. If we are also able to get the scraps back into the circuit, we can in the end make a link between the total metal demand and decompose it into scraps, secondary metal sources, and the primary metal sources. So with that model, now I will present you the results for the European case. Sorry, just going back. So I will detail the hypothesis, the main hypothesis of that model before going to the results. So regarding the electric vehicle sales, the input we have taken is the sustainable scenario development scenario from IEA mobility model. And here, what is plotted here is the electric vehicle sales for all the categories that have been taken into account. So in blue, we have the passenger vehicles, in red, the road freight, in yellow, the 2-3-wheelers, and in green, the buses. And those are the total amount of sales from now to year 2100. Interestingly, in that model, we have the detail between 2 types of passenger vehicles. We have the passenger cars and the light trucks. And also, there's a decomposition between non-urban and urban uses. And we'll see at the end of the presentation how we can make a use of that kind of information. So those are the total sales per year of electric vehicles. Now, if we make a look to different kind of categories and see what kind of engines are used for those vehicles, we have, for passenger vehicles, in dark colors, we have internal combustion engines cars, and we have a switch towards mainly electric cars, and also a small part of it is in yellow is the fuel cell cars. We have the same switch for road freight, even if it's a little bit less weighted towards electric vehicles. We have some more share, higher share of fuel cell road freight vehicles. So in the end, this results in those figures for the annual sale of electric vehicles, considering all the different types. Now, for each kind of vehicle, we have to associate a battery lifetime and the battery capacity. So for the lifetime, we did the very simple assumption that we have 1 battery per vehicle that lasts 15 years. Regarding the capacities of the batteries, the capacities range between 1 kilowatt hours for 2-3-wheelers to 800 kilowatt hours for heavy-duty trucks. If we focus on the passenger vehicles, for light trucks, we have batteries of 100 kilowatt hours, and for passenger cars, for battery electric vehicles, we have batteries of 50 kilowatt hours. Now, if we look at the different chemistries, market share of the different chemistries, we used data from a paper by Chu et al. That has been published in 2020, for which we have essentially 2 types of batteries, NMC batteries and NCA batteries. And for each of those batteries, we were able to associate a material content in terms of kilogram per kilowatt hour. And those data in terms of material content comes from the backpack tools developed by Argonne National Lab in the US, funded by the DOE. At last, we had to define scraps rate and recycling rates. So regarding the scraps rates, it's kind of difficult to have relevant figure or up-to-date figures. We choose to add some pretty conservative rates, ranging from 15% today and up to, down to 4% when the process are improving. Regarding the recycling rates, we have defined two S-type curves that are crossing the European targets presented in the introduction, and that saturates at 60% of recycling. When I say recycling here, it's the combination of the collecting rate and the recycling rate. And we have just different curves for lithium. As we have seen, the targets are a little bit less ambitious in terms of recycling for the lithium. So that was for all the description of the model and the inputs we used. Now we will see the results we obtained for the European Union in terms of battery capacities, total battery capacities that are required to satisfy the electric vehicle demand, and afterwards in terms of metal demand. So here on that graph are presented the total battery capacities that are required to be manufactured to satisfy the deployment of electric vehicles in Europe. So for all the categories we have described, the passenger vehicles, the road freight, 2 to 3-wheelers and buses. What we see is that we have a quite sharp increase of those capacities up to 2030, then slower increase up to 2040, and then after 2040 to 2050, a kind of a plateau. And we reach 800 gigawatt hours in 2035 that are required for batteries, and 75% of which are for passenger vehicles. In 2050, we reach 900 gigawatt hours per year, and 65% of which are for passenger vehicles. So interestingly, we can compare that requirement to the Gigafactories project that have already been announced. And that's what is plotted here in black. Those figures are coming from the batterynews.de website. What we can see here is that the announced capacities of the Gigafactories are high enough to satisfy the European demand. And they are over the demand after 2025. But those are, in black, those are all the announced projects. Not all of them will be effectively manufactured. And if we now look at only the low-risk projects, so the project of Gigafactories that are pretty sure to come to reality, we have figures from transport and environment, and that's the yellow curve here. And in that case, we see that we shortfall from what we need for the European vehicles deployment in Europe. So here, that was the results in terms of battery capacities. Now we switch to the metal content and metal requirement. So on that graph, that's the total metal requirement for all the manufacturing of the batteries, only for the metal listed here, so the main ones of the batteries: lithium, nickel, manganese, cobalt, graphite, aluminum, and copper. And what we see here is that it follows the same trend, of course, as the total batteries, and the metal demand there's a repartition, quite an equal repartition between the demands for the connection of the batteries, the anode content, and the cathode content. Another way to look at that metal demand, instead of looking at element by element, is to look at that by the type of sources. So here it's the same figures, but we discriminate between the primary sources in dark blue, the secondary sources in light blue, and the scrap sources in yellow. Here what we have is that we have a rapid increase of the primary resources demand up to 2030, then a plateau up to 2040, and a decrease of the primary demand up to 2050. And in 2050, in the end, scraps and secondary resources represent about 50% of the total demand. The reason for that evolution is the inertia of the recycling processes, since we have to wait 15 years between a new vehicle sale and the recycling of the batteries. And that's here, I've not mentioned that, but it's without taking into account any second use of the batteries. So here it's for the total amount of metal. We can also look at that metal by metal. So here I'm focusing on lithium, cobalt, and nickel. Two ways to put those figures into perspective. It's to compare that annual demand to today's annual production based on the USGS figures. So if we compare that to today's annual production, we have a peak of demand for lithium, cobalt, and nickel that represents 75% of annual production. For lithium, 60% of today's production for cobalt, and 20% for nickel. We have to compare that with the weight of the European automotive weight, which is 20% of the total electric vehicle sales today, and will be 10% in 2050. So what we have here is that the demand for lithium and cobalt is way higher than our real share of the electric vehicle sales. So probably we'll have an issue of supply here. Another way to put that into perspective is to compare the reincorporation rates to the European targets. So the European targets are in black here, and the reincorporation rate, so the secondary plus scrap sources, is in red. Here what we have is that only lithium will be able to comply with the European targets. For cobalt and nickel, we will be a little bit below the European targets. And that's if we consider scraps into the reincorporation rate. If we consider only the secondary sources, we are even further from satisfying those targets. So what we have is, we see that we have some tension and difficulties to supply electric vehicle market with enough metals. So what we did with our model is we tried to test two different hypotheses in order to lower the metal demand. So those two hypotheses were we have a high recycling rate scenario and sobriety scenario. So the high recycling rate scenario is quite easy to understand. We increase the maximum recycling rate from 60 to 90. Regarding the sobriety scenario, we focused on only the urban mobility, and we said that for those urban mobility, instead of having 100 or pointer does not work anymore. Instead of having 100 or 50 kilowatt hours batteries, we have only 10 kilowatt hours battery. 10 kilowatt hours is the size of two Citroën AMI2. So, and if we do that, here are the results that we obtain. On the left side, we have the annual demand for metals, and on the right side, it's the cumulated demand. If we compare the reference scenario that I've presented and is plotted here in dark blue with the high recycling rate in yellow and the sobriety in light blue, what we can see is that the high recycling rate does not have a huge effect on the peak demand of the metal in 2035. However, the sobriety scenario helps lowering that peak by 45%. However, the recycling rate becomes more interesting in 2045, and it helps lower the annual demand for metals. If we look on the right graph and at the total metal demand, integrated metal demand, sobriety is more interesting up to in 2050, and it's even more interesting up to 2090. It's only after 2090 that recycling becomes more interesting in terms of the cumulative demand. So quite rapidly, the conclusion of that study. So we have designed a model that is quite easy to use to test, to estimate the total metal demand. And what we have seen for the European case is that we will have some tension on lithium, nickel, and cobalt, and that sobriety is the best way in the short-term view to lower that demand. Of course, in the end, the recycling rate is quite important. Here, I don't want to oppose both levers. It's just to compare their relative amplitude. And just to finish, I've just put a picture of what would be the future of the urban mobility versus the past of the urban mobility. So with that, I'm done, and I thank you for your attention.